Welcome to this annual presentation of the SNOW project. SNOW is a 4-year project that's part of a larger program within TNO on applied AI. Within SNOW, we work with around 20 scientists to develop safe, autonomous systems that can operate in an open world. In this presentation, I will give you an overview of the work done within this project in 2022. But first, I will give you some background information about the project. Currently, automation is often used to execute the dull, dirty and dangerous work in known and static environments. And in this project we want to move away from closed and prepped worlds and move towards autonomous systems operating intelligently in an open and real world. Besides, we aim to go from a single purpose to a multi-purpose system that can operate within a team. And to do this, the systems need to have knowledge about the world, about itself and about the tasks, but they also need to be able to learn, because they will definitely encounter situations that they are not trained for. To enable this, we work on hybrid artificial intelligence. This means that we combine data-driven AI, for which we use large amounts of data to train algorithms on and to produce the right output given a certain input, with knowledge-driven AI. And for this we provide a system with explicit knowledge in a knowledge base, which it can use to reason about concepts. By combining these techniques, we can utilize the best of both to act in an open world with other team members. Furthermore, we need a successful ecosystem to implement these techniques in an applied use case. And on this slide, you see the ecosystem of SNOW, which include research institutes, end users with their own use cases, providers of the systems and of the submodules, and integrators to integrate the hardware and the software components. And with the help of all these different parts in the ecosystem, we are able to apply our AI research. And each year we search for a use case to test our autonomy on. And in 2020 we started with the search and rescue use case, where we needed to find people in a mostly known world. And the year after, we made the outside world more unknown by introducing uncertainties and by withholding some information from the system. And this year, we adopt the same techniques in a new use case, the inspection use case, where even more parts of the scenarios are unknown and the system needs to adapt itself to new situations. And this use case will be used in the next part of the presentation as a running example in which I explain our work in a bit more detail. So the autonomous system we work with is a spot robot of Boston Dynamics. And on top of this platform, we build our autonomy. So we created extendable hardware modules called STACKABLES to create a flexible and reusable set of robotic capabilities. And in this way, we can create capabilities per stackable and reconfigure a platform as desired in a mix and match kind of fashion. And this makes our autonomy stack platform and use case independent. And a set of general capabilities was identified which form the servers. So we have the camera server for object recognition and scene understanding, the audio server for communication with humans, and the platform server for localization and locomotion of the robotic system. And all these servers contain a driver that implements the link between the hardware and the software. And to actually execute these capabilities, we developed a behavior executor that combines individual capabilities supplied by these servers into complex, higher level capabilities. And I will go in a bit of more detail about this later in the presentation. So the precise implementation of the type of task the system has to execute in the use case is use case dependent. And for this we need to sit down together with the subject matter experts to discuss what they want the system to do and what not, so that we can specify default so-called plays for the system. And these plays are description of often used activities like a general inspection, but also leaves room for the autonomy to figure out how to execute it within the given constraints and boundaries, of course. And these plays are saved in a knowledge base and are presented to the user as a kind of speed dial for task delegation. And by pressing this speed dial, the user can delegate one of the default plays to the system within seconds. And if a user selects a play, which was created beforehand and saved in a knowledge base, it is on the level of go to each POI, inspect them, and report afterwards. However, for the system to make a plan, it needs to have more details, and therefore we use the knowledge about the environment to create a plan that can be followed step by step. So, for example, including all specific points of inspections. So in this case, it will first go to a specific pipe segment, but also here more detail is needed, because how should the robot exactly do it? Should it crawl or run or sense the environment at the same time? And this is actually up to the autonomy to choose. And therefore the runner will ask the knowledge base how to execute the task in the most optimal way given the current situation. And if it knows the most optimal one, it will send this to the low-level behavior executor so that the system actually can perform the action in the real world. And the behavior executor executes these behavior trees. And these trees describe how to execute low-level capabilities, like for example use a specific sensor or walk to a point or do a specific reading. And these can be executed in parallel or in sequence and with all these different combinations. So one could create a kind of a toolbox of these capabilities by making these different trees, which might be suitable for a wide variety of use cases. And in our use case, Spot can execute different inspections, like inspecting a manometer or a pipe with all these different configurations. And before and while executing a behavior, the system assesses its performance and chooses the best performing behavior given the situation. And it also assesses if it will probably be successful. And to do this, we represent all of these configurations of the system in a knowledge base and recorded a lot of data in different situations. And we analyze the effect of these environmental factors on the performance of each component. And this eventually results in these decision trees that can be used to determine the configuration that provides the best performance for a task in a specific context. But in the open world, it could be the case that we encounter a situation that our performance models are not trained on. And if this is the case, we can measure that the system is underperforming, but since we don't know the cause, we also don't know the solution. And this is why, besides performance assessment, we implemented causal reasoning for intervention. And as you might recall, we already have a lot of information about the system, about the environment that it is in. We have this in the knowledge base. And we do have a lot of recorded data, and we have expert knowledge. And with these sources, we build a Bayesian network, which we use to reason about the cause of underperformance. And for a leak detection, the cause could be, for example, the wind or a noise source, which a system cannot measure because it simply doesn't have these sensors. And after the network reasons about the diagnosis, it will reason about an intervention that will mitigate the disturbance. So if, for example, the system reasons that the wind is the cause of the disturbance, it might want to reallocate itself differently towards the wind so that it isn't a disturbance anymore, and it can do the measurement with a better performance. Another topic we researched this year is the topic of goal-directed perception for mindful inspections. And with this we mean that we want the robot to be able to respond to a finding it gained during the inspection and should try to understand the situation so that it knows a follow-up action to undertake. To do this, the system needs to understand when a situation is wrong. And for this we investigated knowledge-driven anomaly detection. It also needs to know what evidence is useful to collect to understand the situation better. And for this we researched the common sense knowledge base. And of course the system needs to be able to plan for this evidence collection, and for which we research the planning with active inference. And in our use case, Spot might, for example, detect an object that it doesn't recognize to have a role in this normal scenario, which might, for example, be a jerrycan that is laying on the ground. If this is the case, it can ask the user for help by sending a message via the user interface with some information about what is found. And the user can decide if it's worth it to take a follow-up action based on this message. And in this case, a jerrycan might be dangerous in this position and on this side. So the human operator might choose to change the task of the robot to evacuate the site and prevent the jerrycan to cause harm to persons. However, this task is not something that is default for Spot in this scenario, so the play is not on this speed dial and the user has to create a new one. And this can be done quite easily with our delegation GUI. And as this play is created, it is saved in a knowledge base and therefore it appears again in this play menu. And now the user can delegate the evacuation task to the system. So for the system to execute this new play, it needs to be able to do a different kind, more powerful form of planning than we have discussed before. So the plan we saw before was created by a series of instructions, so to say, but as humans can specify different levels of detail within this new play, we use hierarchical task network or HTN planning. And the play that was delegated by the human is converted to an HTN problem, and that's solved by an HTN solver. And this solver could choose a multiple solution to execute the play, for example, by minimizing the time or maximizing the performance. And if a play is executed, the human operator will get a detailed report of the results, and with this, the operator can again decide the best follow-up action.
There is a possible dangerous situation. Please evacuate the area.
So in summary, we discussed the following technology and techniques that we worked on in 2022. We worked on the stackable for more efficient and dynamic configuration of the platform in the use case, the task delegation for more efficient tasking, even if the situation requires dynamic adaptation, the knowledge base that consists of explicit knowledge about the system, the environment and the task so that the system can reason with this, planning in multiple ways to execute the delegated play optimally, performance assessment for effective task execution, causal reasoning for intervention generation if known behaviors don't succeed, and of course goal-directed perception for autonomous information collection about the environment. So in this 4-year project we work on autonomous navigation in the first 2 years and autonomous information collection in the last 2. And in the coming years we want to move towards autonomous manipulation and work on physical intervention a robot could do in the world. And eventually we would like to move towards autonomous system collaborations where systems or humans work together optimally. Well, this completes the presentation of our work in the SNOW project in 2022. Thank you for your time and I hope to see you next year.